Okay, so now we're going to move on to refraction. And when we talk about refraction, we need to talk about the speed of light. So the speed of light is travels at c, which represents 3 times 10 to the 8th meters per second. And I'll just write that in. So c equals 3 times 10 to the 8th meters per second. And so if we think about like a light wave traveling, it travels faster, the fastest it can go in a vacuum. And then when it hits other surfaces like glass, it's going to go slower. And so that's represented here by the peaks of a wave, right? And so they're separated further apart in a vacuum. And then when they get into glass, they're closer together. So it just means they travel less distance in the same amount of time. And so we can represent the index of refraction, which is just a ratio of the speed of light in a vacuum to the speed of light in any medium. And so that number, the index of refraction, changes. One thing you always know is the index of refraction is always 1 or larger. It's never less than 1. And we're going to be using that in when we calculate things about refraction. So let's talk about refraction. So here we have 2 examples. One where we have a light source. So imagine our light source is above here. So our light source is there. It enters the surface. We have theta 1 is our angle of incidence and theta 2 is our angle of reflection. We'll always have some light that is reflected. And so that will have theta 1 is equal to theta 2. But when we calculate our angle of refraction, when we have different indices of refraction, so like air and then glass or air and then water, then the ray will bend towards the normal. So when we go from less dense to more dense, the ray bends towards the normal. So theta 2 will be smaller. Here's another example where now our light source is down here. And again, we have angle of incidence and angle of reflection, usual formulas. But now we're going from less dense to more dense. And so now the ray bends away from the normal. So when it goes from less dense to more dense, towards the normal. When it goes from more dense to less dense, it bends away from the normal. Okay, so how do we do our calculations? We use something called Snell's law. So Snell's law helps us to determine either our angle of refraction or our index of refraction. We can use it by understanding n1 sine theta 1. So that means the index of refraction in our source where we start, where our ray is incident, that's our n1, and our theta 1 is measured with respect to the normal of the surface. So I don't think you can see the surfaces very well here, but I'll give this a shot. So this is one surface, and this is another surface here. And so n1 sine theta 1 would be, say, air, and sine theta 1 may be 30 degrees. And then our n2 would be the index of water. So water is 1.33. And then our theta 2 would be something less than 30 degrees. Same thing here, our index theta 1 is going to be, say it's water, 1.33. And then we're going to have our reflected ray, it's going to bend away. So let's say theta 1 is 30 degrees. I would expect theta 2 to be something more than 30 degrees. I'm looking at different values for index of refraction. We see air is right here. And so we always say that air has an index of refraction of 1 because it's 1.0002. And so we'll just assume air is equal to 1. But we can see we have cubic zirconia is 2.29, diamond is 2.4, glass. So we often use flint glass and crown glass. So we see these two are pretty common in optics for lens making. Ice is 1.3. Water over here is 1.33. So you can just see some of the examples. We usually use glass and water when we're doing our problems in general physics. We also have the case where we have something called total internal reflection. And that's still using the law of refraction. It's just now we have a source. We have a source that's inside our medium. So let's say this is glass. And glass, we know if we have our angle of incidence, our angle of refraction is going to bend away from the normal. And so the bigger our angle gets, so if we started here and moved to the right, these examples, the bigger our angle gets, the more the ray is going to bend towards the surface, away from the normal. And so we get to this case right here where there's a given angle where the angle of reflection is 90 degrees. So what we're looking at is my angle of reflection here is this angle is 90 degrees, right? This is, say, maybe 70 degrees. And this is maybe, I don't know, 45 degrees. So you can see my angle here is increasing. And at some point, for an angle beyond the critical angle, the refracted ray gets beyond 90 degrees and then is reflected back inside. And so how do we figure that out? Well, we can use Snell's law. So we know that n1 sine theta 1 is equal to n2 sine theta 2. But we know theta 2, right? This angle right here for the critical angle is 90. So now we can say n1 sine theta critical. So that's this incident angle right here that matches n2 sine of 90. Now if we plug that into our calculator or look at a graph, we know sine 90 is equal to 1. So that tells us then that sine theta c, if we divide both sides by 1, we get n2 over n1. So that's where the critical angle comes from. And where is this important? Well, anywhere where we're using something like fiber optic technology or an endoscope, things like that, where we want to direct our light and have it stay inside a tube. Let's see if I get off there. Okay, thin lenses. So we use thin lenses a lot in optics to approximate where our image distance is going to be. We can have double convex. So double convex means we have a convex shape on both sides. Plano-convex means that we have a plane on one side and a convex lens on the other side. And convex meniscus is we have two convex surfaces like that, double concave, plano-concave, and concave meniscus. So we can see the example here of converging lenses. So again, we have rays coming in from infinity, right? And they, if we were to draw the ray tracing with our angle of incidence is equal to my, using Snell's law for angle of incidence and angle of refraction here and here, we would be able to draw these rays and see that for rays coming in from infinity, they meet at the focal point. And in a diverging lens, rays come in from infinity, they diverge, but when you project them back, they meet at the focal point, at a virtual point. So here we have F is the focal length, right? Power is the inverse of focal length. So power is just 1 over F. And power is measured in the diopter, right? So that's just a unit that is goes as 1 over meters. Here's an example of rays from infinity that are parallel to the optics axis, whereas this is an example where rays coming in from infinity, they're all still parallel, and they still meet in the focal plane. They're just removed right from the focal plane, from the optical axis. They're just down a distance away, but still in the focal plane. This is ray tracing for lenses. So we did, in the last lecture, we did ray tracing for mirrors, but this is ray tracing for lenses. So notice I have my object here, and my ray comes in from infinity. So it's going this way. And when it hits the surface, we're representing our thin lens with a line. So usually in optics, when you're drawing these things, usually you represent your positive lens with, positive lens like this, and our negative lens would look like this. And we're saying negative. And when we say thin lens, we're usually using this representation. So this would be a the center of my lens, this would be a concave lens, right? Ray comes in from infinity, goes through the focal point, just like for mirrors. And then we can also take a ray that goes through the focal point and comes out, right? This is reversible, comes out parallel to the optical axis. And where they meet is my image. So this is my image. Notice that it's inverted. Oops. And inverted just means, whoops. See if I go back. Okay. Let's see if I erased this. So this is inverted, and inverted just means upside down, right? And we can draw that third ray as we can go through the center of curvature of the lens. So going through the center of curvature of the lens, it goes through straight. It's not refracted, not bent at all, because the ray is striking at perpendicular to the surfaces, and it just goes right through. So that's how we can do ray tracing. We can also use equations just like we could for mirrors, and the equation is the same. So d0 is my object distance, so the distance from my object to the center of the mirror, center of the lens. Di is my image distance from the center of the lens to where the image is located, and f is the focal point from the center of the lens to the focal point. Same with magnification, hi, so the height of my image over the height of my object, and so here, my height of my image, it's going to be negative here, and it's going to be positive here. So I'm going to have a negative value out, and that tells me that it's inverted. I can also say negative di, so di here is positive, d0 is positive. So we add the negative here to tell us whether it's inverted or not. Sign conventions. So the focal length is positive for a diverging lens and negative for positive for a converging lens and negative for a diverging lens. The object distance, if the object is on the side of the lens from which the light is coming. So usually the light, when we draw these, the light is coming from the left and the object would be on the left. So if it's on the left, it would be positive. And otherwise, it's a negative or a virtual object. The image distance is positive if the image is on the opposite side of the lens from where light is coming. So if we have our object on the left of the lens and we have an image on the right, then our image distance will be positive. And our image distance is positive for real images and negative for virtual images. And our image height is positive if the image is upright relative to the object. So the object always defines whether it's positive or not. If it's the same as the object, then it's positive. If it's opposite, then it's negative. The Fermat's principle is just a basic principle, and what it says is that because light travels in rays, right? If I have 2 points, then the path to go from one to the other requires the smallest time interval. So I wouldn't do something like this. That's going to take a larger distance, right? So I'm going to have a straight line right between these 2 points. Of lenses, and so when we add 2 or more lenses in series, the focal length of the combined lenses is given by this formula. And you can see this just means the total focal length of the system is 1 over the focal length of one lens plus 1 over the focal length of another lens minus d over f1, f2. So I have 2 lenses, something like that, and something like this. This lens would have focal length f1, this would have focal length f2. Distance between them is d, and then the total focal length would be, if I were to treat them as 1. So if I were to treat them just as one lens, it would just have length f of the combination, right? And that you would use this equation to calculate it. If you, a lot of times we talk about a doublet, so you can have a doublet that looks like this, 2 lenses together. So I can have something that looks like that, right? And I can calculate the focal length of that combination. And when I do that, my d goes to 0. So here, 1 over f is equal to 1 over f1 plus 1 over f2.